Next is problem 55 from Reading Assignment 4, Section 1.6. The problem statement is like this. We have, the problem statement says, consider the sphere x squared plus y squared plus z squared equals 4, and the cylinder x minus 1 squared plus y squared equals 1 for z greater or equal to 0. And the question asks, find the surface area of the cylinder inside the sphere. Let me sketch this situation. We have a cylinder that's centered on x equals 1. It has a radius of 1. And it goes above the xy plane. We have a sphere of radius 2 that's centered on the origin. I'm only going to draw the top hemisphere because the cylinder we're interested in is above the xy plane. And then I will not draw the intersection just yet because we'll find some more information about it, but we know that here the intersection is here. Intersection, I mean between the sphere and the cylinder. But we know that the fact that there is this sphere means that we're not going to integrate over the entirety of the infinite cylinder. We're only integrating a portion of this cylinder's surface. Let's parameterize the cylinder. We see that it's if it were a cylinder centered on the 0, 0 point, so if we had a cylinder x squared plus y squared equals 1, then the parameterization would be x equals to cosine u, y equals to sine u, and z equals to some other variable v. But we don't have this cylinder. We have a cylinder that's shifted in x by 1 unit. So we need to add 1 to the x coordinate. So I have 1 plus cosine u, sine u, and v. Sine u and v. Let's check that this is correct. What I did here is I took this equation and I plugged in our parameterization. So this would be x, this would be y. So I get x minus 1 squared plus y squared equals 1. Now let's check that this is satisfied. 1 plus cosine u minus 1 has 1 cancelled, so we get cosine squared plus sine squared of u, and cosine plus sine square, if you square both of them, you get 1. Now, now let's get the bounds on u and v. If we wanted to integrate over the entire cylinder, so it would like go to infinity, then we would have u going between 0 and 2 pi, and v would be above 0 because the cylinder is restricted by z greater than or equal to 0. But we also have a restriction that the surface we're integrating needs to be inside of the sphere. So now let's figure out bounds on V, so that this is correct. So the condition inside or on the sphere means x squared plus y squared plus z squared is less than or equal to 4. And this is a mistake, sorry. Now let's figure out what it means for u and v. I plugged in x equal to 1 plus cosine u, y equals sine u, and z equals v, and I got 1 plus cosine u all squared plus sine u all squared plus v squared less than or equal to 4. Then I expanded everything, so I got 1 plus 2 cosine u plus cosine squared u from this, plus sine squared u plus v squared is less than or equal to 4. Then I combined these two things are equal to 1, so I have 1 plus 1 equals 2. And this 2 cosine u is here. And then plus v squared is less than or equal to 4. So then from here we get v squared is less than or equal to, we have 4 minus 2, which gives us 2, minus 2 cosine u. And then after this, we know that this means that absolute value of v needs to be smaller or equal to square root of this. But because we also have this condition, or in other words, this one, we can combine these two things to give us that v is bounded below by 0 and above by square root of 2 minus 2 cosine u. Let's do a sanity check to make sure this is reasonable. Let me sketch this bound as a function of u. But first I will sketch actually without the square root. If we sketch just 2 minus cosine u minus 2 cosine u, we get so this is 2, this is 4. By the way, I forgot to mention one thing. So you see how here I square rooted everything and I didn't think much of it? Well, I did it because I know that this is at least 0. So it's 0 or above. So you know, it makes sense. If this could be negative, then I guess we'd need to be a little bit more careful. Actually, if this could go negative, then like if this were negative, this wouldn't even be possible. Anyways. 3 pi over 2, 2 pi. So here cosine u is, here cosine u is 0. Here cosine u is 2. So then we get 0 here. At pi over 2, cosine is 0. So we get 2. At pi, we have negative 1. So we get 4. So here's our shape. But we know we need to also square root it. So 2 pi, something's wrong. Sorry, 1 second. Okay, so this is the shape, but we need to square root it. So when you square root it, sorry, 1 second. Okay, so we also need to square root this. So the shape would look, well, I guess instead of 2, we're going to have, instead of 4, we're going to have a 2 here. And then the rest of the shape, well, I don't exactly know how it's going to look like, but probably something like this. So I'm going to just cross this out because this was before I square rooted. So actually, this is the bound. So v would go between 0 and this value. Now let's see if this makes sense. Actually, I should have colored it red because this is the... Okay, let's see if this makes sense. So when u equals to 0, which corresponds to, well, on this cylinder, it would correspond to I guess, theta being equal to 0. So we would be, well, okay, so if u equals 0, we have x equals 1 and y equals 0. Okay, so we have that. So it's right here. And we're saying that the bound on v is going to be 0 as well at this point. Then when u increases and goes all the way to pi, we have the bound equal to 2. When u equals to pi, we have x equal to 0, because we will have cosine u equal to -1, and sine of u would be 0 again. So we're just going around all the way to this point. And when we reach this point, the bound is 1. And everywhere in between, we have the bound slowly increasing. So our bound looks something, I guess, like this. And then after this, it starts to decrease all the way to 2 pi. So then here I'm trying to draw the surface that is created by this bound. So below is bounded by 0, so we can also sketch that. So the surface we're looking for is going to look something like this. So then, and then you see this is kind of what we expect if we are talking about it being below the, about it being inside the sphere. Now this gives us the parameterization. So we have r as a function, position vector as a function of u and v, given by what we chose for x, which is 1 plus cosine u. Then y is sine u, z is equal to v. U is bounded between 0 and 2 pi because we want to go a full circle around, and v is bounded by 0 and square root of 2 minus 2 cosine u. We can use this parameterization. We can also use a symmetry argument to say that, okay, it's actually symmetric shape. Whatever happens for y being positive also happens for y being negative. It's exactly the same shape, just a mirror reflection. And you can see it from this graph as well, how the bound is the same whether we're before u equals pi or after u equals pi. So then we can do the bounds from 0 to pi instead, and then multiply the result by 2. And the v bounds are the same as before. That's what I'll do. Okay, now let's, we have the parameterization. Let's find differential surface element. we have Tu equal to, differentiating position vector with respect to u, we get negative sine u, cosine u, and 0. Differentiating with respect to v, we get 0, 0, and 1. Then a cross product is this determinant. We have negative sine u, cosine u, and 0, 0, 0, 1. Taking cross product like this, we have cosine u minus 0, then minus y hat times this determinant. We get negative sine u minus 0, and then we have plus z hat times 0. So we have cosine u, sine u, because negatives cancel, and 0. The differential surface element is equal to absolute value magnitude of Tu cross Tv times dV du. The reason I'm using this, so this is a scalar differential surface element. It corresponds to an area of a patch over which we're integrating. And the reason we're interested in this scalar quantity is because this is a scalar integral. We're going to integrate a scalar 1 over the surface. Now, if instead we had a flux integral, we would not be calculating absolute value, or magnitude. Okay, so we have this vector. Magnitude of this vector is square root of cosine squared u plus sine squared u. So then this is equal to 1. So ds is actually equal to dv times du. Okay, now let's integrate this. We remember how we wanted to multiply by 2 and only integrate for u going from 0 to pi instead of 2 pi. That's what I did. The bounds on u are 0 to pi, as I said here, and then v going from 0 to square root of 2 minus 2 cosine u. The integrand is 1, and then don't forget, so this dv du is without a scaling factor because we've shown that this part is 1. So we've already shown that Tu cross Tv is a unit vector. Now we get 2 integral u to going from 0 to pi of this square root. Then in the next step, I factored out square root of 2 from this. After this, well, I want to say how I got this result and kind of like tell you my thought process, but honestly, I just tried something and it worked. But maybe you could think this way. So I want to do some sort of substitution. I'm guessing that maybe I could substitute cosine u for something, for some variable. So then what I want to have is sine u here, but I don't have sine u. But let's just try to put it there. So what I did is I put sine u there, but then I need to divide by sine u to correct for it. Then I wrote this in terms of the bottom part in terms of cosine. We know that sine of u is plus or minus square root of 1 minus cosine squared u. And because we're interested in the interval 0 to pi, so on u between 0 and pi, we know that sine of u is greater or equal to 0. Because, if you sketch the unit circle, you will have between 0 and pi, you have positive sign. So that's why we're choosing just the plus. Then here's what I did. We have square root of 1 minus some quantity over square root of 1 minus quantity squared. This is the same thing as saying 1 minus a over 1 minus a, 1 plus a. So then I canceled this, and I got 1 over square root of 1 plus cosine u. Then in the next step, I plugged it all back into the integral. So I got 2 square root of 2 as before, same integral. I rewrote this as 1 plus cosine u to the power of negative 1/2 because it's square root and it's in the denominator. Sine u is from here and du. And then in the next step, I just went straight to integrating. You could use a substitution. The reason I got this is because, well, I increased the power by 1, so I got 1/2. Then if I were to differentiate this part, I would get 1/2 coming out. So I want something to correct for it. What you'll also have is cosine u. When you differentiate it, you'll get negative sine u. Sine u is already there, but there is a negative. Sine u is already there. And then since this is going to be negative, you'll cancel with this. Let me just do it. Okay. Negative 2 plus cosine u. I want to show you that when I differentiate this, I'll get the integrand of this. So I get negative 2 1/2 1 plus cosine u to the power of negative 1/2 times negative sine u. So then negatives cancel, 2 cancels, and we get back the integrand. Then I evaluated it at 0 and pi. I got negative. And I also combined this 2 with this 2, so I got 4. And here I got negative 1 plus negative 1 because of pi to the power of 1/2, plus, because there's a negative here, 1 plus cosine of 0 is 1 to the power of 1/2, and this shouldn't be here. And then in the next step, I realized that this cancels. So this is 0. This is 2 to the power of 1/2. So what we get is 4 square root of 2, and then 2 to the power of 1/2, so another square root, and this is equal to 4 times 2, which is 8. So that's it for this question. I wanted to discuss a couple of things. First thing is that this case is a rare case where the surface element, differential surface element, has area of dv du, so there is no scaling factor. That's because we're integrating over a cylinder, and we know that u physically means this angle. So we're changing, du means this in radians, and dv is this, the height. And we know that the radius of this cylinder is 1, and because of this, this arc length is equal to radius times the change in angle. So 1 times du. Now, if the radius wasn't 1, this wouldn't be 1 times du. But because radius is 1, this patch has the area du times dv. I just wanted to give you a heads up for the next question that I'm about to take up. These several questions were taken from the textbook, so you'll notice me referring to either Reading Assignment 4, Section 1.9, which is where you'll actually find this question, or you'll notice me referring to Section 17.5 of the textbook. But you don't need to go to the textbook to see this question. It's all in the reading assignment, actually. Let's do question from the textbook, number 39 from 17.5. This is a true or false question. It gives this statement, and it asks to to state whether it's true or false and to give explanation or a counterexample. The statement is like this. It says that if a single variable function f has a zero derivative for all points x in the domain, then the function f is a constant function. Now this first part is for sure true. We know it from first year calculus. Sorry, one second. So this part is for sure true. The second part, in the second part, the question makes an analogy and says if a vector field f has zero divergence at all points in the domain, then this vector field f is a constant vector field. Now I claim that this statement is false. Let me give you a counterexample. Counterexample like this. Vector field f equals to negative y x 0. I compute the divergence. To get the divergence, you would take the del operator. This is the del operator, dotted with the vector field f. Here I'm expanding the dot product. This is, let me actually highlight it. This came from here. This came from here. This came from here. And then this y is this negative x is here, and this 0 is here. Then computing all derivatives, here differentiating y with respect to x, we get 0. Here we get 0 as well. Here we get 0 because we're differentiating 0. So then overall this divergence is 0, but then this vector field is not a constant vector field. So this works as a counterexample. Therefore, the statement is false. Now let me explain why I chose this vector field. I know that if a divergence of a vector field is 0, then this field doesn't have any source. But this doesn't mean that the field can't have rotation. And actually, in this case, this vector field does have some rotation, which sort of means that for sure it can't be a constant vector field. Let me sketch the xy trace so you see what I mean. The z component of this vector field f is 0. Let me actually copy this vector field here. We have vector field f equals negative y x 0. Okay, so the z component is 0. So we just need to sketch y and x components. You can do it two ways. You can just look at a whole bunch of points on the xy plane and then just go ahead and sketch the vector field at all of those points. I like to do it slightly differently. I get the magnitude of the vector field. I see that it's equal to y squared plus x squared. So this is equal to the distance from the z-axis. Or you could say r, distance from the z-axis. Here r is the cylindrical coordinate variable. I also look at the dot product between the vector field f and our hat vector. This one would be negative y x 0 dotted with x divided by square root of x squared plus y squared, y divided by square root of x squared plus y squared, and then 0. This is the cylindrical coordinate r hat vector. Now, if this doesn't look familiar, you should check the reading assignment 0. There is some more details on how to get this r hat. And this dot product is equal to 1 over square root of x squared plus y squared times the following. We get negative y times x plus x times y plus 0. So then these two terms cancel, so you get 0. So we know that at any point on the xy plane, when we sketch our hat vector, our vector field is perpendicular to it. So this would be my r hat. And then my vector, you know what, this looks huge. I'm going to make it smaller. This is r hat. And then the vector field either goes up or down at this point. Now let's figure out up or down so that we know whether the field is going clockwise or counterclockwise. So at this point, for example, this is a point with some x coordinate and then y equals to 0 and z equals to 0. We have f equal to, okay, so y coordinate is 0, so we get 0, like negative 0, then x, and then 0. So if x coordinate is positive, then the y component of the vector field is also positive. So we get the field going this way. And now we can just sketch the rest of the field. We know that it will always go perpendicularly to the r hat. So r hat goes this way, and then the vector field goes at 90 degrees, and we've figured out the direction of this vector field. And then you can check that we sketched it correctly by plugging in all those different points into the expression for the vector field. And the magnitude of the vector field is as large as the distance from the z-axis. So something like this. And then here it's like this, like this. Okay, now why am I sketching this? I'm sketching this because clearly this field doesn't look to have any source, and we've just proven that it doesn't have any source. Its divergence is equal to 0. But the field has some rotation, which is why I've selected this as the counterexample. Now you might be wondering what happens if both divergence and curl are 0. So this is 0 curl and 0 divergence. Actually, in this case, you can still have a non-constant vector field. Example would be like this one. Let me compute divergence and curl. You'll see they are both 0, even though this vector field is not constant. Let me show you the actual calculation. Sorry, all this stuff just appeared on the screen. The reason why is I was gonna actually do it with my pen, but then it's too much work. I just ended up pasting typing the formulas. Okay, divergence of this vector field is the del operator dot product with the vector field. Here you see I copied it exactly. This is equal to partial x of the x component plus partial y of the z component, y component, plus partial z of the z component equal to, this gives us 2, this gives us -1, and this gives us -1. So we get 2 minus 1 minus 1 equals 0. So you see the divergence of this field is 0. This field is not constant, okay, but also, surprisingly, curl of this vector field is also 0. The reason why you can think intuitively curl will only take derivatives sort of like cross derivatives. So x component will be differentiated with respect to y and z, but not x. So if it's just a function of x, then this doesn't contribute to the curl. Same for this guy, I made it a function of y only, and same for this one. But let me show you the calculation. Curl is sort of a cross product between del operator. You can see it's right here. So this part is the del operator, and this part is the vector field F. And then we take this determinant just as we usually take a cross product. So we get x hat and then partial y of -z minus partial z -y. Then we get minus y hat, and then determinant of this matrix, we get partial x -z minus partial z of 2x, and then we have plus z hat times the determinant of this matrix, so it's partial x -y minus partial y 2x. This is equal to, let's see, this derivative is 0, this derivative was also 0, same for this one, this is 0, this is also 0, this is 0, and this is 0. So overall, we get a 0 vector. Okay, let's do the next question. Next part is part B. It gives you the statement that if curl of a vector field is 0, then the vector field is constant. This statement is false, and we've actually just shown that this is the case. I'm reusing, for the counterexample, I'm reusing the vector field I had in the discussion, in this caution part for part A. You see 2x, -y, -z. It's not a constant vector field, but it has 0 curl. We did already the calculation. So this was part B. Now let's do part C. In part C, the statement is like this. A vector consisting of parallel vectors has 0 curl. This statement, I will claim that this is false. As a counterexample, I will use vector field F equals y, 0, 0. Let me sketch the xy trace to sort of explain why I think this field has non-zero curl. So this one, it only has the x component, and the x component is positive when y is positive, and the x component is negative when y is negative. And also, the magnitude of f increases when y becomes also larger in magnitude. So let me sketch that. Positive x for y greater than 0, and then the bigger y is, the bigger the magnitude. So this looks something like this. And you see these vectors are all parallel. But by looking at the picture, you can tell that this field sort of has a rotation. You could imagine that this field is rotating counterclockwise. Looking from the point of view where I'm looking. Let me show you. So I will make a claim that this field is rotating sort of in this overall direction. So the axis of rotation, you could think of it as being into the page. So I claim that the axis of rotation for this field is into the page. This way I'm claiming that this field should have non-zero curl. Axis of rotation. Okay, let's do the calculation. Again, curl of the vector field F is a dot product between this del right here and the vector field F. Let me compute it. For the x component, we get this determinant. This would be just 0 minus 0. For the y component, I put the minus already here. And I would take this determinant. So I get 0 minus this derivative, partial z of y. For the z component, I have this determinant. I get 0 minus partial y of y. This is equal to, here I get 0. Here, actually, I get 0 again because this derivative is 0. So the only thing left is this. This derivative is 1, so I get negative z hat, which actually has to do with these axes of rotation going into the page, so in the negative z hat direction. The main thing is this curl is non-zero, even though the vector has parallel vectors. That's why the statement was false. Now let's do part D. The statement is this: vector consisting of parallel vectors has zero divergence. This statement again is false. Counterexample would be f equals to x 0, 0. Let's sketch this field. The field again has only the x component, and this component increases when x becomes larger. So we have this. This vector field looks something like this. And then for larger x, the field becomes stronger. So you see it still consists of parallel vectors. And just by looking, it's actually has negative x component when x is negative. But just by looking at the picture, you see that it has some sort of a source, right? Because it visibly diverges away from, let's say, the x equals 0 plane. Let's compute the divergence. Again, del operator dotted with the vector field, and we get this partial x with respect to x gives us 1, then plus partial y with respect to, partial y of 0 gives us 0, and then this guy gives us 0 again. So we get 1, which is not 0, which makes this a good counterexample. The next statement says that curl of f is orthogonal to f. This statement is false. Let me explain why. So to get a counterexample, let's first consider this field f1 equal to negative y x 0. We already sketched this field. It looks like this. And let's compute its curl and see what it is. Again, we have the del operator, we have the vector field f, negative y x 0 from over here. For the x component, we get this determinant, which is 0 minus partial derivative of x with respect to z, but that's just 0. Then for y component, for y component, I already put this negative here. And then we have this determinant, which gives us 0 minus, we have, so this negative, and we also have partial derivative with respect to z of y, which gives us 0. For z component, we get this determinant, which gives us partial x of x is 1, and then we have minus partial y of negative y is negative 1. So then the result here we get 0, 0, and here we get 2. So then this is 2z hat. So then you'll say, okay, well, that's not a counterexample in any way, because this vector field f1 is parallel to the xy plane, and this curl is in the z direction, right? So actually, this is an example, not a counterexample. But let's see here. Let's add z hat to this field f1. So let's construct our counterexample by adding f1 and z hat. And now let's compute the curl of this. Curl of f, by linearity of the curl operator, will be curl of f1 plus curl of z hat, right? Curl of f1 we just computed, it's 2z hat. Now curl of z hat is 0, because curl of any constant vector field is 0. And also you can check this by just computing it. I'll do it on the side. Curl of z hat equals to this determinant x hat, y hat, z hat, partial x, partial y, partial z of 0, 0, 1. And then you see every time you'll take this sort of product of derivative and a constant number, right? So then all those derivatives will be 0. So then in the end, you'll get just 0 vector. Okay, so this is curl of f. You could have computed just by first adding f1 plus z hat and getting the curl. Okay, this is curl of f. It has a z component. It's actually just in the z direction. And this vector f has a component in the z direction. So actually, these two things cannot be perpendicular. So this is a counterexample. We can also check. We can take a dot product, F dotted with curl of F. This will give us 2z hat dotted with F1 plus z hat. We know that F1 is parallel to the xy plane, so this dot product will give us 0. And then this dot product will give us 2. So then overall this dot product is 2. So the two vectors, this one and this one, are not perpendicular. So this is the last part of this question. Now let's do the next one.
This is exercise at the end of section 2.2.2 in reading assignment 4 part 2. The question asks you to show something about two different components. I'm only doing the Z component. The Y component is very similar, so I'll leave it up to you to try. Now, I really suggest that if you haven't already looked at the discussion in the reading assignment that leads up to this exercise, I really suggest you look at it, because otherwise the problem statement wouldn't make sense.
Okay, let me start. But first, let me remind you how to find components of curl. So you have a curl of a vector field. The vector field has three components, fx, fy, and fz. You would have this del operator components over here. And then the x component you would find, but I only want to focus on the z component, so I only expanded out the z component. So x, you would do this determinant. For y, you would have a minus and then this determinant, and for z you'll have plus and then this determinant. So I got partial x of fy minus partial y of fx. Now, in the reading assignment, you've learned an alternative way to figure out curl of a vector. And alternative expression is given by this. There's a mistake. Is given by this. It's a limit as az approaches 0 of a line integral over cz hat of f divided by the area, where, let me explain what each of those things is. You have an area. Let's say it's just a square. It's z directed, that's why I'm calling it az hat. So the normal vector of this area is directed in the z hat direction. And contour cz hat is like this. It's a closed contour, and it's directed in a way that's consistent by the right-hand rule. So if you align your thumb with the normal vector, you will get the direction of the contour. So this is the corresponding contour cz hat. Now, this expression is saying that if you're interested in curl of a vector field at this location, what you want to do is, for the z component, for example, you would set up an area that is in the z direction. You would figure out how much the vector field is circulating on this contour, and then you would divide it by the area that's bound by this contour. And then to find the x or y component, you would do the same thing, but you would direct the area in the x or y direction. So for example, in this case, let me draw the axes. We have x, y, and z. This would be to find curl of f in the z direction. In order to find curl of f in the x direction, for example, you would set up a contour that is normal to the x hat. So your contour is like this. And you would see how much the field is circulating on this contour, and then you would normalize it by the area of this contour. And for the y component, same idea, but now the normal vector would be in the y hat direction. Okay, so now, oh, and by the way, the x component is explained in the reading assignment, so you can take a look. And now I'll explain what to do with the z component. And the task that I'll focus on is to show that this expression is equal to the same thing that we had when we, so basically to the conventional way of finding the curl. Now let's, to solve this problem, first let's assume that we're looking for curl at some point x naught, y naught, z naught. I'm doing this just so it's easier to write things out. Now this point, you can place it either at the center of all the way around. So you can place the contour in such a way that it goes around this point, so the point ends up in the center of the contour. That's what I originally drew, but to be consistent with the reading assignment, I'm actually just going to place the contour in such a way that the point is in the corner. So here I'm showing you a top view of this situation. You see the z-axis would point out of the page. I made the x-axis go to the right and y-axis go up. And the point of interest is right here. Now let's understand what's happening to the integral. This integral is made up of 4 parts, one corresponding to each segment of the contour. First segment I placed at x equals to x naught plus delta x. This is this segment. Delta x is the x dimension of this area, and I will make delta y the y dimension of this area, and this was from before, sorry. Okay, now the unit vector in the direction of the contour is like this. It's t x naught. Oh, great. Plus delta x. I will put a hat here because I can't boldface it. And hat usually denotes unit vectors, so it makes sense. The second contour is here, c x naught. It's located at x equals to x naught. The unit tangent vector is called tx naught, is pointing in the negative y hat direction. This integral is from this contour, c y naught plus delta y, and the tangent vector is in this direction, t hat y naught plus delta y. And the last integral is at this contour, c y naught. And t hat y naught is the corresponding direction unit vector. Now, by the way, you'll notice this was the closed contour integral because it went around a closed contour, but the individual integrals are over open contours. That's why I don't have the circle symbol here. Next, I did two things. First thing I did is I realized that, for example, this vector is in the y-hat direction, positive y-hat direction. So when I take a dot product with f, I'm only sampling out fy component of this vector. And the fy component in this case, since we are on this contour, is going to be at x naught plus delta x at some y, whatever the y value is at any of the points on this contour, and then at z naught, and then z naught. Now, if you're not convinced that this dot product is equal to fy, I can, for example, explain it in several different ways. One way is to realize that my t x naught plus delta x equals to y hat. That's because it's a unit vector that's pointing in the positive y hat direction, so it must be y hat. And we know that when we take a dot product between a vector and y hat, we're going to get its y component. And you can see it just by expanding f as fx, fy, fz. And then when you take a dot product with y hat, you'll get the y component. If you're still not convinced, for example, that this t at x naught plus delta x equals to y hat, for example, you could think back to how you were parameterizing contours. So you could think, okay, my contour over here is parameterized in terms of y. So the position vector here is a function of y. And then when we're trying to find the differential length element, which is r prime of y dy, we're going to get what? Well, the position vector on this part of the contour, let me put another cloud here. So on cx naught plus delta x, the position vector as a function of y is given by x naught plus delta x, y, and then z naught. So this, what I'm explaining in this cloud, is the most, how to say, not brute force, but like it's the most similar to how you are usually evaluating things in line integration. This, I was giving more of a geometric argument. I just looked at the contour and told you what the direction of the unit vector is. Either approach is totally fine. I'm explaining you several approaches so that if one doesn't convince you, maybe the other one will convince you. Okay, so this is your r of y, and then as a result, r prime of y is going to be 0, 1, 0. And dy stays as before. So we get y hat times dy. So you see that this is equal to y hat times dy, so t hat must be equal to y hat. That's another way to explain why this is the case without involving geometry. So for the rest of the integrals, I will not do all of these different computations, but you can if the way I explain as I go along doesn't convince you, you can go back and try to redo any of those explanations yourself. Okay, now let's deal with this second contour, which is the one over here. On this contour, t hat x naught is pointing in the negative y hat direction. So what we'll end up getting here is a negative y component of f. Again, it would be at x equals to x naught, at y being whatever the y value is at any of those points, and z equal to z naught. Here we will get, this part is on this contour. What we'll get is f negative fx at x y naught plus delta y and z naught. Yes, and this is a mistake. This should actually be x. 1 second. I want to try to fix it without crashing my computer, because then they'll have to start over. Okay. All right, and the last part is this one. This dot product is over here. Our t vector points to the x hat direction, so we get plus fx at x, y naught, z naught. Let me actually sketch these components that we just figured out. So I will not sketch the full f. I will just sketch the component that's important. So here, the component that's important, no, maybe I'll start with this one because it corresponds to this order. We have plus fy that's important, right? Over here, it's negative fy that's important. On this contour, it's negative fx that's important. And on this contour, it's positive fx that's important. Okay, now let me, that's not the only thing I did. Another thing I did is if you compare these two lines, this set of lines and this, you will notice that I replaced y with y naught right here, and I did here I replaced y with y naught. Here I replaced x with x naught, and here I replaced x with x naught as well. Here's what I'm doing here. I'm realizing that we're interested in the limit as the contour becomes very, very small. So az hat approaches 0, or actually more precisely, delta x approaches 0 and delta y approaches 0. Now, if this contour is becoming smaller and smaller and smaller, the field along each of these contours, along each of the segments of the contour, doesn't vary much. So we have that fy at as a function of y on this contour, yes, on this contour. Now I'm talking about this one. On this contour, fy as a function of y doesn't change much. So I can just evaluate it at this point right here and pretend that it continues to be the same everywhere along this contour. Now for this contour, I did the same thing. I said that let's just evaluate it at y equals to y naught and not worry about the variation of y component of the field along this line. And the smaller your contour becomes, the more precise this approximation is. Here I also did the same thing. On this contour, I evaluated the field, the x component of the field at this point. So I plugged in x equals to x naught. And this is a mistake again, sorry. So is this. And then on this contour, same idea. I evaluated the x component of the field at this point. Okay, next I realized that each of these quantities inside the integrals are now constants because this is just the component of the vector field at a specific fixed point. It no longer varies here on this along this line. So now we are allowed to take this out of the integrals. Once we do that, we are going to get this here. We will get the integral to be the same as before, except without this part. This negative goes here. This goes outside the integral. The integral stays as it was. This part you see is now outside the integral as well. And this is what's left of the integral. This part ends up here. And this integral is here. So then in the next step, I evaluated what each of the integrals are. For example, this integral is the length of this contour. This length is equal to delta y. This contour has length delta y as well. This contour is the one over here, has length delta x. And the bottom contour has the length delta x as well. On the next step, I factored out delta y because you see we have fy at some value. Let me just highlight it. We have this fy minus this fy times delta y. So I factored it out. I also factored out delta x and this negative. And what was left was fx. And then this, but now it goes with a minus because I factored out a negative. Then on the next page, this part, I just copied it over. Oops. And I took this part and plugged it into the expression for the curl. You see how the curl is the limit as az approaches 0 of, oh, by the way, I made a mistake here. I'll fix it in the notes, but actually, it's like this. Because az hat is right. Okay, so so we have the integral, the contour integral, divided by the area of this surface. And we need to take a limit as delta x and delta y approach 0. Here, this like this as well. Here, I copied over what I got on the previous page. This is just that. And then I divided by delta x and delta y, which is the area. And now you see that if I split this into two parts, one corresponding to this and another one corresponding to this. If I do that, I'll be able to cancel delta y for this integral and delta x for this integral. And now you'll see that this expression looks very familiar because this is just the partial derivative of fy with respect to x. And the second part is the partial derivative of fx with respect to y, because you see it's at y naught plus delta y minus value at y naught divided by delta y. So that's all there is to this question. I realized as I was explaining that actually there is a discussion for 2D vector fields that looks very similar to what I just explained. But I hope that since my explanation probably isn't identical to the reading assignment, maybe you would get some better understanding once you see both explanations.
Let's do exercise 9 in reading assignment 4 part 3. The question asks you to prove a vector identity. Shown right here, it has 3 different terms, 2 on the left-hand side and 1 on the right-hand side. The way I proved it is by expanding everything out into its components. Let me just explain a little bit what each of those terms has in it. One thing you'll see is C dotted with a del operator, and then all of this is followed by this vector B. Now, when you see something like this, you need to be a little bit careful because you see a dot product, but and you're probably used to seeing that two vectors, when you take a dot product, can be swapped. Well, it doesn't work like this with a del operator. You can't just swap it with other things. This is kind of analogous to a situation like this. If you have, let's say, what we have here is similar to having a function, and then you have a del operator, so kind of similar to a derivative. Or let's even make it simpler. Let's make everything function of one variable. So you have a derivative, and then it's like this, and then it's followed by something else. Well, what this means is that you will be applying this operator to g. So you need to differentiate g, and you need to multiply the result by f. It's not the same thing as writing df by dx and then multiplying it by g. They are not the same quantity. So don't just swap derivatives and things that visually look as if they multiply it. Well, actually, in this case, they do multiply it, but yes. So just be careful. Don't swap del operator with anything. Okay, so here in the first term, right here, I've expanded out vector c into its components. I've expanded out the del operator, also the components. I also expanded the b vector. Maybe I'll use a different color. The vector b is here, and we have vector a right here. Next, I expanded out this product over here, and I got this expression in brackets. So you see cx partial x plus cy partial y plus cz partial z. And then as before, we have the b vector and the a vector. Next, I expanded out everything that you see in this big bracket. So the result would be a vector because we have this scalar operator expand into each of the components. So this just goes here, here, and here. It acts kind of the same way as it would if you had a scalar multiplying a vector. But in this case, it's an operator multiplying a vector, applied to a vector. So we have this operator and then bx, the operator and then by, the operator and then bz. Let me highlight the components of the b vector. So here, here, and here. And again, we have the a vector in the dot product here. Next, I've expanded out each of the components of the vector on the left-hand side. So you see like this, and like this. And then you can see that the bx ends up over here, and over here. Then I do the same thing for the y component, and so then you see this by ends up here, here, and here. And the same thing for the z component, here, here, and here. And as before, we have this a vector over here. Okay, so next, I expanded this dot product. So now everything works pretty much as before. You can see that ax multiplied with this x component gave me these three terms. You can see ax is here. And then we have cx partial bx dx. This is over from here. Then this term is here. This term is here. You can see the same thing happened to the y components. I have ay and this ay over here, multiplying everything that is right here. So we have ay, ay, and all of these things I just pretty much copied. And then same idea for az. It multiplies these three guys. So here, here, and here. Okay, so that's it for this term. Now let's work on the second term. So this one has, this one's a bit simpler. So it just has a divergence of the vector b and this simple dot product c dot a. So c dot a is just cx ax, cy ay, cz az. Oh, by the way, this is component 2, like part 2. And then the divergence of b is partial x bx plus partial y by plus partial z bz. And this has three terms multiplying the other three terms. So in total, we will end up with 9 different terms. Let me show you in a bit more detail. For example, this partial x bx is right here with this whole thing. And then we have, again, this thing multiplying partial y by. And then again, that same thing multiplying partial z bz. Next, I just expanded out all of this, and same for all the other terms. Let me just convince you that I did this correctly. So you see cx ax right here, partial x bx plus cy ay partial x bx. And then same thing for z. And then I wrote, I expanded this out, so cx ax. So you see the cx ax, cy ay, cz az are all multiplying this guy. And same idea here, we have cx ax, cy ay, cz az multiplying partial z bz. So this is it for this term, and now let's figure out how to expand the third term. So this would be, oh no, sorry. Not this yet. Let's figure out what happens when we subtract the two. Maybe green. So when you subtract the first term and the second term, here's what you get. So here I copied the first, what we got for the first term. Sorry, this was from the first term. This was from the second term. And then you will notice that a few things will cancel. They are the ones highlighted. So you can see that there is the cx partial x bx ax. This also appears in the second term right here. Same thing for y. There is cy ay partial y by, and then same thing for z, cz az, and then partial z bz. So these guys cancel and everything else stays as before. You know, if you want, you can check that I copied everything correctly. And then, so this is it for the left-hand side. And then let's expand out the right-hand side and show that they are the same. So this would be term number 3. And we just want to make sure that we just want to verify that whatever 3 expands into is this expression that I got right here. So let's do that. So this, I copied this third term. You can see it has this A cross product del operator. It's again, it's kind of similar to how we had this C dot del operator, but now it's cross del operator. So once again, don't try to swap the two or things like that. I'm expanding this. You write this determinant as you do for cross products, and then you take this product, you get ay partial z minus az partial y, all of this for the x component, then minus y hat, and then you have this product. So you get ax partial z minus az partial x, and then plus z hat, and this product right here, ax partial y minus ay partial x. So this is it for this part. Next, I took this cross product with b right here. So here you can see I copied the x component. So whatever I got here, I copied over here in the second row. And then these 3 things are the components of the b vector. And then as before, we take the cross product. So for the x component, you get, let me actually use maybe a highlighter. So you get, so for x component, you want to get determinant of this matrix. So you can see we get az partial x minus ax partial z times bz minus all of this. So ax partial y, ay partial x times b applied to by. And then same idea for y. So we have minus y hat and then determinant of this matrix. So we have ay partial z minus az partial y applied to bz minus ax partial y minus ay partial x bx right here. And then same idea for the z component. Maybe I'll use this. So we get z hat and then determinant of this matrix. So we get ay, partial z minus az partial y applied to by right here minus az partial x, ax partial z applied to this bx. So we're almost done. We already figured out this guy, and now we want to take a dot product with c hat. So here again, I copied whatever I got over here and took a dot product with sorry, did I say c hat? I meant c. So then you can see this guy is, so it's whatever we got here. So this would have this x component. You can check that they are the same. This is the x component. This is the y component. And this is the z component. And I take a dot product. Well, there's also this minus over here, this one. And then I take a dot product with c. This would be that. So this would give you cx, cy, and cz. Remember, result of a dot product is a scalar. And then you just expand. There isn't much happening here. Let me just go over it so you can try it on your own. So you see, I grouped everything with a plus in one bracket and everything with a minus in the other bracket. Let me show you. So cx, az, partial x, bz is, right here. Then this goes with a minus, so we have minus cx, ax, partial z, bz. And then we have minus again, cx, ax, partial y, by, right here. And then this minus and minus gives us plus, so cx, ay, partial x, by. And then same thing here, so minus this whole product. So we get cy, ay, partial z, bz. Next one goes with a plus because of these two negatives. cy, az. And then this partial y, bz. And then minus and minus gives us plus. So again, we have a term here because of this and this, partial y, and then bx. And then we get minus, that's overall minus, so it goes into this bracket, cy, ay, partial x, bx. And then same things with cz, so we get cz, ay, partial z, by. and minus CZ AZ partial partial Y BY, then minus AZ CZ partial partial X BX, and then minus minus gives us plus, so CZ AX partial partial Z BX. So then I just copied what we got on the previous page, and if you compare them term by term, you'll notice that they are exactly the same. So you see I've grouped here. We have again also a grouping of all the plus terms and all the minus terms, and if you go one by one, you'll notice they are the same. Let me actually highlight them and show you. So AX CY partial partial Y BX, this would be AX, yeah, so this would be this guy right here. Let me use another color, maybe yellow. Okay. This is that. Then we have CZ AX and partial partial Z BX. This is over here. CX AY partial partial X BY. CZ AY partial partial Z BY. Oh, sorry, this is that. So what is this then? Sorry, this was right here. And then we have CX AZ partial partial XBZ. CY AZ partial partial YBZ. So this is all for the plus. Now for the minus, we have CY AY partial partial XBX. CZ AZ partial partial XBX. And then CX AX partial partial YBY. CZ AZ partial partial YBY. CX AX partial partial ZBZ. And CY AY partial partial Z BZ. So really, this question is very straightforward. The only tricky part is dealing with the del operator. So as long as you understand what rules apply to the del operator, you should be able to do this question, no problem. The rest is just a little bit tedious, but conceptually it's not too difficult.